This is the very first lecture of aircraft performance. In the first chapter, we are going to study the atmospheric modeling and effect. So the first part is the atmosphere. First of all, we need to find why we need to study the atmosphere. That means the importance of the atmosphere towards aircrafts. So first of all, because the aircraft is flying within the atmosphere of the Earth, so the performance characteristics of an aircraft depend on the properties of atmosphere. Also, the variation of air temperature, pressure, and density with altitude are particularly important because aircraft are flying at different altitudes for different missions. So the change in air temperature and pressure and also its density will exert a lot of effect towards the aircraft performance. So normally we can have temperature, pressure, and the density of the air, and then to be more concrete, TP rho will influence the aerodynamic lift and the drag of the aircraft, and also because although we have electric aircraft nowadays and also it's evolving, but for conventional aircraft, the engine fuel air mixture, that means the combustion efficiency, will also be decided by TP rho. And if you are flying propeller-driven aircraft, so the propeller efficiency will also be influenced by temperature, pressure, and density. Just now we were told the temperature, pressure, and the density of the atmosphere at different altitudes will influence the aircraft performance. And as a part of thermodynamics, I believe most of you have done the module of thermodynamics. There is a relation between Tp and a rho, so it's called ideal gas law. Rho equals P divided by R times T. So that relates the three properties of the air. Okay, you may wonder what is R. R is called gas constant, and for air it equals 287, and with a unit, I'm not reading it. And the value of R varies, changes slightly depending on the molecular composition of air at a particular location. So it changes, but overall the variation is not very significant. We can take it as a constant. But for different type of gas, R is different. For example, and the R for nitrogen and the R for oxygen are completely different. And the addition of water vapor to air reduces the density of air. And because the density of water vapor is 0.013 kilogram per meter cube, and it's much smaller than the density of air, which is 1.225 at sea level. So if you add water vapor, if the air is humid, and the density will reduce. So this is qualitative analysis. Probably we already know when we were at a younger age, like primary school or middle school, and the Earth's atmosphere is divided into several layers. And this diagram gives a clear organization of the layers of the atmosphere. So from the Earth's surface, we have the troposphere, which is the environment where we are living, the human beings are living, and we have the weather phenomena in the troposphere, and also a lot of turbulence, gusts. But above the troposphere, which is quieter, that's the stratosphere, where the most of the aircraft cruises in this layer of the atmosphere. And then above the stratosphere, we have the mesosphere. And above the mesosphere, there's a thermosphere. And above the thermosphere, we have the exosphere. So thermosphere is really the edge of the atmosphere. Okay, and this diagram also indicates the typical activities that taking place in the atmosphere. So we can have a look. And because the aircraft can only operate within the troposphere and the stratosphere, so later on we will focus on these two layers. Okay, first of all, troposphere. And troposphere is um, from the Earth's surface to the tropopause. Tropopause is the ceiling of the troposphere, and we already know most of weather conditions takes place in the troposphere, and we have gusts and turbulence, right? And since at the beginning we were interested at the pressure, temperature, and the density of the air in the Earth's atmosphere, so temperature in the troposphere decreases at a nearly constant rate of 6.51 Kelvin per kilometer. So it's a constant rate decrease of the temperature, but for pressure it's different. Pressure decreases exponentially with increasing altitude. So every 18,000 feet or 5.6 kilometers, there is a 50% reduction in pressure. And for example, the altitude of Tibet is about 5 kilometer altitude. So the pressure over there is about 50% of the pressure we are experiencing. And a lot of people go there and will suffer the reaction due to the loss of pressure, right? Okay, the tropopause, we know it's the ceiling of the troposphere. And interestingly, because of the temperature difference and also the atmospheric activities, the North Pole has the troposphere at the North Pole has less altitude than that in the equator, and that is according to this diagramming here. And the troposphere at the North Pole has an altitude of about 7 kilometers, but we can see the tropopause at the equator has an altitude of about 17 kilometers, which is significantly higher than at the North Pole or South Pole of the Earth. Okay, and if we look at the other stuff in the diagram, we can see there is a why. We may wonder why the altitude of tropopause is higher, because at the equator, the air is engulfed to a higher altitude that pushes the tropopause higher. But at the North Pole or South Pole, the air is engulfed downwards. So that's why the tropopause at the poles has smaller altitude. And above the troposphere, we have the stratosphere, and the stratosphere extends from the tropopause and to about 50 kilometer altitude. So, and we know the stratosphere is different from the troposphere because it's quieter. There is no turbulence, no gusts. So that's why our aircraft would like to cruise in the stratosphere. Okay, the temperature, also we are looking at the temperature and the pressure in the stratosphere. The temperature remains constant to an altitude about 25 kilometers, after which afterwards it gradually increases with altitude. So instead of decreasing, it will increase above 25 kilometer altitude. This is because there is absorption of the ultraviolet rays from the sun by the ozone in this layer, because the ozone in the stratosphere, and it will absorb the UV light from the UV sunlight from the sunlight, and that makes the temperature in the stratosphere, that part, higher temperature. Okay, the pressure, and of course the pressure decreases with increasing altitude. And the stratosphere is free of gusts and turbulence, but it is characterized by high steady winds, the jet stream. So this this jet stream makes the flight time different. For example, you are crossing the Atlantic, and so from, for example, the UK to the US, the way forward and backward, we have different time if you've done the flight before. That's because of the jet stream. Aircraft typically cruise at stratosphere, as I said. This is to avoid turbulence in the troposphere and makes a flight smoother and a better experience, and also safer. Now we are looking at the atmosphere above the stratosphere, and the next is the mesosphere. And the mesosphere extends from the stratopause to 80 to 85 kilometers altitude, which is pretty high. The mesosphere is a layer where most materials burn up upon entering the atmosphere. Because of this burning, and that makes our Earth safe from the intruding materials, right? And again, temperature decreases with height, reaching around minus 85 degrees C at the mesopause, and the water vapor is frozen into ice clouds. Okay, then we have the thermosphere, which is also called ionosphere, and it extends up to 500 kilometer to 600 kilometer. This region is bombarded by extremely shortwave radiation from the sun, and populated by ionized atoms, which align with the lines of force of the Earth's magnetic field. The ionization of oxygen and nitrogen releases photons, which may be visible as aurora or the northern light. So this is the thermosphere, and beyond the thermosphere is the exosphere. The last layer is called the exosphere. The lower boundary of the exosphere is called the exobase. It is also called the critical altitude, as this is an altitude where barometric conditions no longer applies. And this is because there is not enough air inside. Strictly speaking, this is space. The altitude of the exobase ranges from about 500 to 1,000 kilometers, and depending on solar activities. And a Hubble Space Telescope orbits at an altitude of 547 kilometers, so it's just above the Earth's atmosphere, so it's in the exosphere. And temperature in the exosphere becomes nearly a constant above the altitude. So that's the temperature in the space. In the end, we can have a look of the video of the highest free fall from 39 kilometer. This takes place in which layer of the atmosphere? Give you 1 second. Yes, it is stratosphere. And this is the stratosphere is also the altitude where the balloon can go to. Okay, let's have a look of this video. It's from YouTube. So it's the field, the balloon is filled with, I believe, the light gas, maybe nitrogen, and so it will lead the capsule to the height, which is in the stratosphere.
Release.
If you're scared, walk away. 'Cause there's no need to feel ashamed.
So this is highest free fall, and at that height we can already see the curvature of the Earth. And the jump took a few minutes, I think. We can already see the curvature of the Earth at this height, 39 kilometers. Which is really exciting.
Jumper away. Speed 725. Showing Felix in a stable descent. And Felix is back to it safely. The new world record.
Okay, so this part of the lecture, we went through the different layers of the atmosphere, and also we know how the temperature and the pressure changes within those different layers, and they have also their features. But for aircraft performance, we are looking at the stratosphere and troposphere most of the time, because aircraft won't fly beyond the stratosphere. But for space engineering, we need to cover the whole range of the atmosphere.